So I assume everybody's here and we can start then our discussion session. I did prepare a couple of general slides to put this all into a context, considering that we have a relatively limited session and didn't cover all the potential topics that could have been discussed in the context of QCD in external magnetic fields. So there were quite a few people in the session who actually gave the motivation quite clearly. And I'll just have to perhaps briefly put the highlights on my interpretation of this all to keep everything in the context. So we do have a very, very vast range of external magnetic fields that could be relevant for the physics in the early universe. In particular, that we could have magnetic fields well over the QCD energy scale. And in this case, we might even start talking about generically gauged theories in external magnetic fields. And there are a lot of interesting topics in this direction. Not this session, I guess, did not cover much of that, but there were mentions of external magnetic fields, or I should say primordial magnetic fields in the early universe. Of course, there is the appearance of strong magnetic fields in the context of heavy ion collisions. This is basically the relevant scale. Here we have the magnetic fields potentially on the order of the QCD scale. And of course, that's where the interplay might be the most dramatic and visible. At least one Ephraim mentioned about the application of magnetized QCD matter to the physics of compact stars in the context of magnetars. In particular, we would have sufficiently strong magnetic fields to affect the strong interactions and perhaps modify the underlying physics. And I think it was sort of between the lines that many people talked about this, but somehow nobody maybe explicitly said. I always believe that strong magnetic field is a very interesting theoretical tool to simply study confined gauge theories, understand how the confinement happens, how the chiral symmetry restoration happens, and an additional tool, controllable tool, at least theoretically, is very useful to have at our disposal. And I think that's why we can also consider studying QCD in magnetic fields as a very potential direction of research. So considering those potential directions of research, there is a large list of those that have been covered today. Chiral symmetry, of course, and here all the words magnetic catalysis, inverse catalysis, and all of that fall into this category. Deconfinement in QCD with a magnetic field, how the dynamics happens, the polarcal loop affect, interact, and modify due to the presence of the magnetic field. The properties of baryons and mesons in strong magnetic fields. Again, we had several speakers that touched on that topic, and we had a lot of that in the discussions in the chat. So we perhaps want to come back to that in the further discussion. Thermodynamic properties of magnetized QCD matter. Of course, it will have relevance to some properties of stars, perhaps, early universe, maybe some other places. In either case, this is something that can be addressed and perhaps with the lattice calculations most reliably. Transport properties, there was very little on that, but the transport properties of magnetized matter will be also modified, obviously. Emission, particle emission and absorption in the context of heavy ion collisions, in the context of early universe, perhaps. This will be a reasonable topic to address in the presence of the magnetic field. The appearance of new phases in strong matter, strongly interacting matter in a magnetic field. Ephraim again mentioned something about that. But I don't think anybody addressed the potential modifications of collective modes in magnetized QCD or even in vacuum. And of course, anomalous properties of magnetized QCD matter. chiral magnetic effect, chiral separation effect, and many of those things will appear in the context of heavy ion collisions. So in general, the presence of magnetic fields and their effect and their evolution in heavy ion collisions, which is of course a relevant topic that is becoming pretty, well, it is already pretty hot in the studies of heavy ion collisions. So on the right, I sort of briefly added the names of people who were touching at least on those topics. As you could see, there are some of those in between left that didn't seem to be touched greatly, at least today. So I guess we could look into them in the discussion if needed. But before we go there, I sort of want to direct this discussion also in a slightly more physics direction, that what kind of physics questions we are trying to address by doing this calculations and these studies. So of course, in the context of magnetars, how the magnetic fields could affect the properties of the stars, how they change their properties, how they change the observational features that come from the stars. Is the magnetic field sufficiently strong and long-lived in heavy ion collisions to affect the physics that is happening there? There is a lot of discussion of the effect of magnetic fields, but of course one has to address the sort of the lines, the main question sitting in front of us, whether they are actually there and they long enough to affect that physics. Can we infer the value of the magnetic field from heavy ion collisions? What kind of observables we should look for and how to probe those properties? So basically it's one of the things that may need to be sort of kept in mind. How to test those numerous anomalous properties due to chiral anomaly in the presence of magnetic fields that are triggered by the magnetic field. We do know that there are a number of potential effects, but so far mostly experimentally they were measured in solid state physics, ironically, not in heavy ion collisions or any other high energy physics. So basically that remains a question. Recently, there was also a lot of interest in multi-messenger astrophysics. And of course, that became super popular in the context of stellar mergers, compact star mergers. There are obviously magnetic fields there. There is magnetohydrodynamics that is at work at the main part of the evolution of those mergers. So how big is that effect? Some astrophysicists who study magnetohydrodynamics say that that's not a little effect and potentially magnetic field could play a very important role. Are there any promising anomaly and plasma instability that could lead to a spontaneous generation of magnetic field in early universe or in compact stars? There were some proposals and apparently there are some promising indications that that's possible. But again, this is something that is of interest to address in perhaps more detail and seek for some experimental verification of those facts. And of course, in the end, we are trying to look perhaps for some novel effects triggered by magnetic fields in all of those contexts. So what they are, what can they be? And I think some of those have been briefly mentioned in the talks. So there is no very well-defined structure for the discussion that we want to have, but I would like to have something along the lines that touch at least roughly 3 different categories. One of them is the model calculations. We spent the first 3 talks touching on those topics. So I suggest that we go into some details, try to figure out what is the strong points there, what are the weaknesses, where we are heading, to what degree we can rely on those models, how to improve them. And of course, some of the talks, they have been specifically going in that direction. So we perhaps could find some compromise and see what works, what doesn't. How to supplement those models as Gergo marker said in his talk how to extract those coupling constants from the lattice calculations reliably and how to compare them properly to the effective models. And of course, again, how to find some new predictions and insights from effective models. I don't want to be negative, but unfortunately, most of the effective models these days, they are trying to reproduce the lattice results, but very few of them try to sort of make the next step and actually do predictions that perhaps will be difficult to do with the lattice calculations and in the directions that might be, well, extending the reach of reliability. Of course, the direction of the chemical potential is one of those promising directions, but perhaps that's not the only one. There are a lot of questions regarding the lattice QCD calculations, and we could, again, perhaps touch on those topics, underlying physics, what is driving, what is a deconfinement driving an inverse magnetic catalysis, or the magnetic field is actually modifying the confinement, and that in turn is sort of reflected in many different effects. So that's basically something that I suggest we could also mention. Of course, there is a big question, and I suppose that might be difficult because of the limitations of lattice with the non-zero chemical potential, but even very small chemical potentials could potentially lead to, in combination with the magnetic field, could lead to anomalous physics. And I would like to also kind of raise the question whether lattice is capable of extracting some of those. And of course, in addition to this, two techniques that are, roughly speaking, effective models and lattice calculations, we could also try to think about other tools, theoretical and experimental. So on the theoretical side, you could think of hydrodynamic approaches, kinetic theory, maybe even some new approaches that come from the combination of, let's say, some correlators in quantum field theory from first principles and so on. And of course, on the theoretical side, which experimental data could help us to understand the physics in magnetic fields a little bit better, maybe give some additional thought food for our discussions. So that's roughly kind of the big picture that I've seen. And with that, I wanted to start with some sort of general discussions of the effective models. And I see that there are a couple of hands raised. And I didn't see who was first. On top, I see Ricardo's page, so let him start.
I understand the criticisms to effective models of QCD, but in just an example, we have a prediction of a jump anti-mod for the pole mass of the pion. Mm-hmm. And I know that I'm not a LATSI guy, but usually LATSI evaluate the screening mass. But if you can touch the pole mass, they can compare with our predictions.
That's actually was something very natural. And I would like to hear sort of from lattice calculations about this as well, because it's true in effective models, pions seem to be, well, mesons in general seem to be relatively easy to calculate. Comparison with those could be very natural. In lattice QCD without magnetic field, I know that that lattice works fine for mesons. So that, I believe, was one comment in the lattice talk by Gerger saying that pions are difficult, and I was kind of stumbling on that. If you could maybe clarify that.
Well, what I meant was that you also have to take into account the disconnected parts there. So, and that's not very obvious in general.
And when you're saying disconnected part, I mean, you could calculate the pole masses of pions, right?
Actually, not disconnected, connected parts. I'm sorry. So I meant that. Okay, maybe if the other Gergi wants to explain it better,
should I comment on that?
You can probably do that better. Yeah.
Go ahead.
Yeah. So usually when you look at 2-point functions of some composite field on the lattice, then you have different contributions, connected and disconnected. Connected means that you just have one diagram connecting the different quark fields inside the composite field. And disconnected means that you have just a bubble on the source side and the bubble on the sink side. And these disconnected type of diagrams are very difficult to calculate because of noise problems, basically. And one thing is that when you go from zero magnetic field to non-zero B, is that these disconnected terms appear also for the neutral pion, for example. They are absent at 0B, but they are there at non-zero B, and they make the calculation complicated. And this is actually something I wanted to point out whenever you compare to these lattice data for pi U and pi D. This is not the full story. This is a comment that we make in all of our papers, but maybe I should emphasize it here as well, that this is not the neutral pion. It's a hypothetical meson, which is only a U bar U state. And we can also look at a hypothetical meson, which is a D bar D state. But it's not the real neutral pion. In order to get that, you have to actually look at these. Can someone turn down the micro? I'm having an echo.
Yeah, if you're not speaking, could you please mute the mic? And then when you're speaking, you will turn it on.
So just
because we start to hear the echo. So
you can do that on the lattice, and I think this should be done, and that is not so complicated to be done. And by now we have both the algorithmic and the computational techniques to do this. One should calculate these disconnected diagrams on the lattice at finite B, but at this point they have not been yet calculated, and therefore a comparison directly with the neutral pion is not so straightforward. So that was one reason for why we looked at baryons instead of mesons.
Well, but you might have seen the. Go ahead.
I just want to clarify. So when you say that the disconnected diagrams become, when you have magnetic field, they become dependent on the magnetic field. How is that? Is through magnetic moment interaction? How is that they become dependent on the magnetic field?
Basically, the disconnected diagrams vanish at zero magnetic field because of isospin symmetry, that you can exchange an up quark for a down quark. It turns out that they have terms that come with opposite signs and they cancel each other. Now, when you go to non-zero B, you have the different electric charges for up and down, and they don't cancel each other anymore. It's just that. It's just that. There are these terms, but they cancel each other. So if you look at the eta meson, for example, which is not the triplet, but the singlet in the light quark pseudoscalar channel, then you also have these terms at 0B. At finite B, actually, there are not too many lattice calculations that consider this. I mean,
I suppose it's mostly unknown how big they are. That's why they're in trouble, I suppose. Is that right?
As I said, at non-zero B, I'm not aware of any calculation that did this, but it could be done. I mean, it's just someone has to sit down, code in, implement them, and then generate a couple of thousands to millions of configurations to have a good signal.
Actually, there is no this problem for charged mesons, right?
For charged mesons, you don't have a problem because then only connected terms are there. And therefore, for charged pions, this is always okay, and this is
right. And actually, for charged rho, the small magnetic field limit provides the value of gyromagnetic ratio 2 from one side, and for large B, there is no zero mode because naively one one may expect that there is a zero mode and superconductivity, but so it disappears. So this is latest result of several years from now. Yeah.
Yes. So for charged vector mesons is the same. There things work out fine. For neutral.
So why don't you compare pion masses with the charged pion masses with the NGL model?
Right. So our intention was to look at hadron states for which the most naive model gives no change in the mass, so no change in the energy. So if you look at the possible Landau levels, then for a charged pion, you know that you have this Landau level enhancement of the mass of the charged pion, or of the lowest energy of the charged pion is just m² plus b, right? And so there is this basically trivial effect in the quark in the mass, and we didn't want to look at that. We wanted to look at something more which comes beyond that. We might have tried to subtract this Landau level contribution to the charged biomass and then look at corrections on top of that, but we thought this is that would be actually a subleading effect. If you look at just the proton or just the neutron mass, then the simplest effect is just no dependence on the magnetic field, because the lowest Landau level for fermions is just independent of the magnetic field, as you know.
Well, actually, there is something more on this, but I think there is a hand raised. So maybe before we continue more with the lattice, Nuxar, you have hand raised.
Thank you. I have a proposal. We today several times mentioned the linear sigma model or its part, now well-known pion nucleon theory of U cover, where that constant, pion nucleon U cover constant, if we combine in fine structure constant, is about 15. It's big. But theory formally is as good as quantum electrodynamic or QCD, if you like, because it is renormalizable. But the constant is big. It is really strong coupling constant by starting. During 50 years, that constant extracted from phenomenology, experimental data, monotonically decrease toward the value of 13. If we take exactly 13.0 and put this coupling constant in Goldberger-Treiman relation, this relation fulfills with precision less than 1%. So we have very good prediction for that constant. Thing is that in the numerical simulations, we can calculate that constant of behavior of the constant for low energy limit. So it's a good problem to calculate strong coupling. This is phenomenology. This model is in the part of the phenomenological models of QCD, but it is good by itself. It's renormalizable and so on, in difference with the sigma model, for example.
I'm sorry to interrupt, but does it have to do with this effective models that have been used today? Because what you're talking about is about the physics without any magnetic field.
Nuclear physics is mainly
without magnetic
based,
field or with magnetic field.
Oh no, it's
unclear.
Magnetic is extra effects. Of course, it's important also that model. If it is for the Nabuena-Lazionio model is important. It is more important to estimate that effects in the Yukawa theory. Yukawa theory is working tool for nuclear physics, for pion potential and so on. But this is a really strong coupling constant problem and may be solved by contemporary level of computational culture simulations and so on. The second thing is also from the side of condensate physics, graphene. In graphene, the speed of light or coupling constant, effective coupling constant of quantum electrodynamics is about 2. It's just measured, but with not good precision until now. They are not good motivations. We can also calculate by numerical simulations that coupling constant And for that coupling constant, we have also good suggestion idea that it is 2.0. So these two problems are fresh. No one calculated, touched. They are important problems and manageable to calculate today. There are some hints why 2, but let me save it because of less time. I have not much more time.
I'm afraid you're taking this in a slightly different direction, and I'm not sure exactly where it's leading. So what's the bottom line?
These two problems are similar. They are strong coupling covalent, similar to the QCD strong coupling problem and with extra magnetic field control parameter. Magnetic field is an external control parameter, very good control parameter. We can change controllable way this parameter and study matter. So it's important. It's important not for only for QCD, but many other problems. And for the graphene and for the nuclear physics, beyond nuclear, it is very important. So we can use the knowledge tools of this QCD magnetic field culture and use there. Somehow that problem.
I'm afraid this is done already. This is done already.
Oh, no,
routinely.
No.
Igor, if I may jump into this.
Absolutely.
Go ahead.
Fresh.
I cannot raise hand because I am still the co-host, but
yes, you're in penalty zone, but go ahead.
I think that I understand what Naxar is trying to point out to. He is pointing out to a very important issue about how to fix parameters when it comes to effective models of QCD applied in the context of magnetic field calculations. So this is actually something that I believe this community, the effective theories community, needs to pay attention to. Because see, if you come from the field in which you're just computing using one of these effective models, vacuum properties, then of course what happens is that the best values of the coupling constants turn out to be huge, like this that Naxar was mentioning about. But then what you need to remember is that in the context of vacuum, for instance, the linear sigma model has been used to describe nucleon properties, and therefore the large values of the couplings are related to the large values of the nucleon masses. So, but see, there is nothing that prevents you from using the same model, say the linear sigma model or the Nambu-Jones model, in the context of matter which is mixed, in other words, hadrons with quarks. And the hadrons in this case are mesons. And the quark fields are taking the place of the nucleons. And because of that, and because of the masses, in this case, of course, effective masses of the quarks are smaller than the nucleon masses, then the couplings become smaller. And so it is true that, they are still large, but they are not that large, and they need to be fixed in such a way that you describe certain physical observables. So there are attempts, and our group has made some attempts to fix them, resorting, for instance, to the critical temperature of the chiral transition at zero chemical potential, baryon chemical potential, or this kind of ways of fixing them. But it is an important aspect that Naxar is touching upon. The way you fix the couplings should be such that it describes some phenomenology. There are some attempts, I want to stress, but nevertheless, the point is well taken, but it depends on the context. And when you come up to describing quarks, then the couplings are not that large, Naxar. I think this is it.
Okay. I see that Norberto was trying to jump in, but couldn't. Go ahead. But you have to unmute yourself first.
Okay, thank you. I have a couple of questions concerning Markos talk, because I think it is interesting in the sense that it tries to connect model calculation to lattice QCD calculations. However, I think he assumes in his calculation that the nucleon mass is just given by the sum of the three masses of the constituent quarks. This is kind of a strong approximation. People know how to calculate the baryon mass taking into account the binding energy of the nucleon. And this was not taken into account. This is one thing. The second thing, I would like to see again, if it's possible, his plot of the proton mass as a function of the magnetic field, because it seems to me that it starts rising. So it looks like a small magnetic field. The proton mass goes up in his lattice calculation. And I think this is in contradiction with Cara perturbation calculation.
You could try to share that if it works.
I can try to, but then I think you have to.
It's fine.
Stop
if it goes. Oh, I have to stop first. I see. Okay, I did.
Where is it? Yeah.
I was actually also puzzled about the fact that you ignore the interaction between the constituent quarks.
Okay, so about the first point, so of course, this is a very simplistic way of looking at this, but to be honest, it's really hard to say to what extent do you need to take into account interactions, because so on the one hand, you want a strong B dependence, or at least to see that there's a B dependence. And on the other hand, okay.
Well, if I may interject, it's a very simple thing. It's like the fight of the good and the bad. You're taking only one of those, the fact that the constituent masses are changing, but the fact that the coupling is changing is also meaning that their binding energy will be changing. The effect is actually there, and you know it's there because you are saying the coupling is changing with the field.
Yeah, but
so that's, I believe, what Norberto says.
That's why I'm afraid that I am afraid of its conclusion that he can get the coupling constant out of this calculation.
Because, can I comment on that?
Yeah, sure.
Go ahead. The other Gerger.
Clearly, you can do a lot of different things, and you can improve on this constituent quark model, which is really the simplest thing that you can do. You can improve on this. So what we considered was, what happens if you do this simplest thing, and then the results come out right? You can now change this model, how you get from constituent quark masses to baryon masses by including baryon binding energies. You can also make them be dependent. Then you have more parameters. I can imagine that you will also be able to describe the results nicely, just because you have allowed more freedom in some sense.
No. I believe it's different. We all do some approximations. It's not a problem. And you do the simplest first. It's fine. The thing is there at least a naive reasoning to expect that this is okay? Because what Norberto says is that actually there could be a very big effect due to the that coupling, because the coupling itself changing dramatically the binding energy, and you say, no, it's not a big effect. So we have to resolve the sort of the problem.
But I mean, okay, I think the simplest way to resolve this is to perform the calculation with the binding energy P dependence taken into account and look at what is the size of the term that we neglected. I agree that we neglected the term. I just don't know by heart whether this is really that large. I would have expected the opposite.
Well,
so in our definition, the mass is really just taken as the lowest possible energy state, adding together constituents with a given mass, and this is just the sum of the masses. So I mean, I know that you can cook up a very simple quantum mechanical model also for the binding energy, but then in some sense you are starting to take into account the magnetic field dependence in that, and we wanted to push that magnetic field dependence in the G. I can imagine that maybe you arrive at the same result when you put the G dependence, the B dependence in the binding energy, and for that you get a different G of B. But maybe for the condensate you get something similar. I suggest someone to do this exercise and compare.
Well, we did.
I mean, in this context, with the comparison to the lattice.
We did a calculation in the number general linear with a constant G, and we also get decrease in mass for the proton and for the neutron.
Yeah, but so Norberto, can you give us qualitative understanding how big this effect is compared to the constituent mass effect?
At small magnetic fields is rather strong, because what happens is that you construct the nucleon with a diquark and a quark. And a quark binding energy is rather strong at the beginning for low magnetic fields. So it somehow managed to counter-effect the fact that the masses is growing. So you have the mass growing, but the binding energy also grows. Because usually in the number-general model, you have an increasing mass with the magnetic field.
So how large is the binding energy? It's 10 MeV.
Well, it depends, of course, on the coupling constant.
Yeah, but I mean, the order of magnitude is...
on the diquark coupling constant. But then,
am I right that the order of magnitude is...
You don't know exactly how large it is, but you can get some idea, I mean, from fierce transformations, for example. So you know it's around the same value as the isoscalar coupling constant.
Okay. Well, it's kind of obviously a difficult task to extract all different effects. So I guess in a way both are right. So Gerger's right that the first approximation, you just neglect that and then try to see whether it works or not. But of course, it would be ideal if sort of the order of the effect could be understood better, and then this sort of uncertainty will go away.
Can I nevertheless have a follow-up question to this?
Yes. There is like three raised hands, okay, sorry, and I just wanted to give a chance to somebody else to jump in, and then we will return back to this if there is an opportunity.
Sure.
Sergei Nedalko, you were the next, I believe.
Okay, thank you. I think I will show up myself, and maybe we'll switch off just to reduce the flow of internet. There is a nice question on your transparency, how to improve effective models. No, and it's obvious that improvement would be in the inclusion of confinement of dynamical quarks. Otherwise, it's always cycling around the chiral symmetry, and there is no connection to what Massima was talking about. And might be, don't consider it as a kind of self-advertising, but just to attract attention. Yeah, I will drop to the chat with a couple of references.
Well, some people, you including, were doing this, right?
Yeah, no, in a sense that if we are talking about external magnetic fields, then we may think about the possibility to describe the basic QCD vacuum properties also in terms of some certain typical mean field. And a good candidate seems to be, yeah, such a kind of Lamprey background field of abelian self, anti-self dual fields. This really goes back to Lloyd-Wheeler and some old times. And then, what the first reference given there, in principle, all qualitative features described by Massima at the end of his talk can be rid of this mean field approach. No, might be that I will stop here because otherwise I would need to tell much more.
No, actually, it's a very good point. Perhaps sort of for the general information. Of course, this is one of the approaches that exists. There is also Polyakov loop modifications of NGL model, and there are so many other modifications. And I believe it is indeed extremely important to keep in mind that there is that confinement. And in fact, you have a, well, not a passive player here. And Massimo mentioned about that anisotropic deconfinement and stuff. In fact, we are raising this issue since 2002. This is really something that you could do perhaps partially in QCD directly, but no. I guess this is sort of taking me on.
No, might be so if possible. I will add one word more, that the idea. So it's that it's extension of this hadronization picture to some non-local on one hand, such that there is a gluon exchange. So it's not NGL, which is local, and then taking into account certain background fields which provide for the absence of physical quarks. Yeah. And then what the effects which were described by Massimo, they are read off as when you switch on external magnetic field, electromagnetic or electromagnetic fields, they start to influence on the character of the dominating gluon fields. And finally, they may just change their character to such a way that color charged quasi-particles start to appear and to become physical degrees of freedom and so on and so forth. So it goes in this direction. Of course, there are many technical problems which are almost unmanageable, but nevertheless, it's a kind of point of view. Thank you. That's my comment.
Well, there are some other raised hands, so let's go there first, and then we may return to this. Vivian. Vivian, we cannot hear you. Yeah.
Yes, yeah, thank you. I just want to, I don't know if the topic is so interesting for the group, but it's part of, you know, related to what the things you mentioned and to the title of the section, which is QCD phases in magnetic fields, right? So you mentioned the importance of collective modes in the presence of a magnetic field. Actually, we spoke, I mean, Efrain spoke about that, but he had to go very quickly at the end because of short time. But actually, I think that, first of all, one area that we haven't discussed much, but it's also very important, is how do we manage to pinpoint phases that are theoretically proposed at conditions that we cannot measure. So for example, very high densities and low temperature. We are talking a lot about temperature, and it's very important and very interesting, but what about neutron stars where the temperature is not so relevant? So how do we pinpoint what is a phase there? The only way, I think, is by astrophysical observations. So those phases have to go through certain steps, check mark, I would say, that just say, okay, it's not in contradiction with this observation, it's not in contradiction with this observation. And I wanted to call attention to these inhomogeneous phases with topological properties that seems to check mark a lot of those constraints. And so I just want the colleagues to think about that, because this is in another area of the QCD phase map. But for example, this MDCDW is just one phase. It could be another. I mean, I'm not saying this is the lowest energy phase, but it's not in contradiction with the two mass observations. It survived the Pierce instabilities. Why? Because it has a magnetic field, and a magnetic field, being an external field, creates, modify the coefficients in the expansions of the fluctuations and make them to not to erase the condensate pretty much after you have final temperature. That's what Pierce said. But on top of that, there are other coefficients that are topological and make the phase even more stable. So I think that's a very interesting property of this phase. And now with what Efrain presented, we just found that it might even explain something that is known and is a big puzzle in astrophysics, which is this missing pulsar problem. So I would say, I mean, I'm not saying this is the last answer, but I think that my proposal is that in cases where we don't have experiments that we can test things, we have to just check observations and how they agree or not. And I mean, the community is doing that, but not just equation of a state. That's what I'm trying to say, but new constraints that can come from different set of observations. And that is another way for us to decide, understand what is the phase that realizes in regions that right now we cannot reach by any experiment. That's what I want to say.
Right. No, it's actually an excellent point. That's what I was trying to drive at as well. There are many regimes where there are a lot of models and people could basically cook up anything. But if you don't have any kind of input, that is physics, it becomes just fantasy world. So basically that's what I was trying to say. Even lattice calculation, it's like a sort of mini experiment in a way, but if you don't have lattice, chemical potential, astrophysics is perhaps one of the ways to go. So I probably would completely support what Vivian said. And I see though that there is a question related to this I assume, from Ricardo to Efrain. Is that axion the same as that appears in Pache-Quinn approach?
What?
You can see the chat message, right? It's there. Or Ricardo, you could tell it yourself.
Yeah, I can do this. There is a possible candidate for dark matter that people call axion, that is the Goldstone boson, that can be included using Pache-Quinn approach. And that axion that appeared in your seminar is the same thing, or is other possible axion? Sorry, it's a naive question.
Yeah, very good question. Yeah, this is something very close. That is the idea. The models are not the same. The problem is that they also propose an action field, and even the idea that the missing pulsar problem can be solved with dark matter is already in the literature. But the only problem there is that then they have to explain how this dark matter that is filling the whole universe is not also making the other pulsars to decay, that is to collapse and then they have to propose a very big gradient, you see, of variation of dark matter from the central galaxy place to the other places that are far from there. Then this is something in discussion. People are able to go in that direction. And
although clarifying question, since you're talking about this, just to clarify, in the center of the galaxy, there will be a lot of stuff, and basically there could be a lot of accretion. So one might say, why not more accretion, less pulsars, more black holes?
Yeah, that's the idea, that because of the attraction of the black hole that is in the center of the galaxy, it is expected, you see, that the density of pulsars will be higher. But at the same time, there is a big activity of gamma ray bursts. Then the two things together are the one that we are using for our model. In the dark matter model is a different thing. That is, what they say is that the center of the galaxy is attracting too much dark matter, and then the dark matter is trapped in the core of the neutron star, and also can produce the collapse. But are two different ideas in that sense. We are using.
Yeah, but it's good to point out that this is not the regular dark matter. This is dark matter produced by the collective mode coming from the background of the phase inside the
I guess
core.
you don't want to call it dark matter.
No, no,
It's
no.
not dark. I mean, you know, when we saw this, I wanted to call dark matter, and my friend said, no, that would be wrong because people would think that we're talking about the same. And he's right, it's not the same. This is related to a phase that exists there. But the effect that it produces essentially is it increases the mass of the star and eventually can collapse it. So it's not dark matter in the usual.
The polariton is only created in the core, you see?
Only
and
created.
Dark matter is coming ready from outside. It's coming, concentrated there, and then producing the collapse. And here, that's not the way. Here you have like a bombarding with gamma rays that then becomes inside the core polaritons. And it's something very interesting because you have then two particles that are massless. You have the phonon and you have the photon. And then through the anomaly, they can produce this massive polarity. Yeah, it's something very weird, no? It's not the common thing that we see in other models.
It's a collective mode. As Igor was saying, it's a collective mode, directly related to a magnetic field. You don't have magnetic field, you don't have the action polariton. And
in all these problem, the magnetic field is playing a very important role. That is, we don't need a critical field to produce the
connection is a bit.
If you don't have a magnetic field, then you have the Landau-Pierce instability, and then you know the fluctuations will destroy the condensate. But the magnetic field prevents this big fluctuation to take place. Then that's the real role of the magnetic field in this problem. It's not like you need a critical field in order to produce a condensate or something like that.
Well, okay. I'm getting the message that we should probably start wrapping this up. And I guess this might be indeed a good point to do so because already half of the people left anyway. And it's actually local time apparently pretty late. It's good for me, but not for everybody. So I guess at this point, I'll just say, sort of reiterate what I was trying to say. So we could try to look into different types of physics in the case of QCD, but we shouldn't lose the sight of sort of where we are heading, sort of physics applications, testing it against different types of approaches, different types of methods, lattice QCD, effective models, experiment, all in the mix, and try to find some interesting phenomena. And I guess that's basically all what we need to do. And with that, I think we are ready to stop this.